Hi everybody. In this video I want to look at the plot for the position as a function of time for a mass undergoing simple harmonic motion. So one way we were able to write our general solution for the position as a function of time for a mass oscillating in simple harmonic motion is cosinusoidal function. So x equals, the position x equals the amplitude times the cosine of omega t plus phi. Now I want to show in this video, one of the things I want to show is that this omega is the angular frequency. So now let's provisionally assume that, and then we'll check it as we go along. So if omega is the angular frequency, it should be related to the standard frequency this way. The angular frequency is 2 pi times the frequency. Frequency and period are reciprocals, so the angular frequency will be 2 pi divided by the period. All right, so rather than looking at this full-blown general solution, let's look at a special case where this phase angle, phi, is equal to 0. So with that special case and making the substitution that the angular frequency is 2 pi divided by the period, this equation would become x equals a cosine 2 pi over the period. So the capital T it represents the period. That's a constant, whatever that period is, multiplied by little t, which is just time. OK, so what we're going to do is we're going to plot this and see what comes up. So I'm going to plot it over here. I'm going to plot time on this axis. I'm going to plot x on this axis, and this will be x equals positive a. This will be x equals negative a. All right, and I'm going to plot it two different ways. In a few minutes, we're going to look at x in terms of the position in terms of a sine function rather than a cosine function. And we'll get there in just a moment. With regard to the cosine function, I'm going to plot it on this dotted axis. So this dotted axis and this dotted axis here. So as time's going this way, this will be 0 time. This will be 1/4 of a period. This will be 1/2 of a period. This will be 3/4 of a period. And this will be 1 full period. OK. So that's the scale. We'll use this other scale when we're looking at the sine function. All right, so let's fill in this table. When the time t is equal to 0, I'd have 0 times stuff gives me 0. Cosine of 0 is 1. 1 times a gives me a. So when t is equal to 0, the position x will be equal to the amplitude. All right. When the time is equal to the period divided by 4, I'd have 2 pi divided by the period times the period divided by 4. This will give me, that multiplying those together will give me pi over 2. Cosine of pi over 2 is 0, so I'll have x equals 0. All right, when the time t is equal to capital T over 2, that is, when the time is equal to half of a period of the motion, I'd have 2 pi over t times capital T over 2. That overall is just going to give me pi in here. Cosine of pi is minus 1. Minus 1 times a gives me minus a. All right, when little t is equal to 3 times the period divided by 4, that is 3/4 of a period, I'll end up with 3 pi over 2 in the argument of the cosine. Cosine of 3 pi over 2 is 0. And 0 times a is 0. And finally, when the time, little t, is equal to the period, capital T, I'd have 2 pi over capital T times capital T. That'll just give me 2 pi in the argument of the cosine. Cosine of 2 pi is 1. 1 times a is a. So let's plot this. I've got it over here. So remember, this is our x-axis. This is our time axis. And we're using the dotted axis right now. All right. So at time 0, here's the location for time 0, x, the position x will be equal to the amplitude a. So we'll plot that point right there. Now, when the time is 1/4 of a period, x will be equal to 0. So time of 1/4 of a period, x is equal to 0. Plot that point there. When the time is equal to half a period, the position x will be minus a. Go down here, right about here. That's x equals minus a. This is time equals half a period. When the time is 3/4 of a period, x will be back to 0. And finally, when the time is equal to 1 full period, x will be equal to positive a again. And we can just connect all those up. I'll just do that with a dotted line. This will be a very approximate sketch of a cosinusoidal function. I probably should have had that point down a little lower, but it's close enough. All right. Now, we know that a sine function is just a, so first, let me verify this idea. We provisionally assumed that the angular frequency, that this omega is in fact the angular frequency, which would mean it's equal to 2 pi over the period. Well, let's just check. Does in fact the mass go through one full oscillation in one period? Well, what happens? At time 0, the mass is at x equals a. At time 1/4 of a period, the mass has gone down. At times half a period, the mass is all the way down here. At 3/4 of a period, the mass is back up to x equals 0. And then at 1 full period, it's back to where it started. The mass has, in fact, gone through one full cycle of motion in one period. So this provisional assumption that the omega symbol there was the angular frequency is in fact correct. OK. Now, a sine function is just a shifted cosine function. So I could have made a separate plot, but what I wanted to do is actually just shift the axis. So for our plot of our sine function, and again, we could have a general solution, x equals a sine omega t plus, inside this argument of the sine, some phase angle theta. Well, let's set that theta equal to 0 and just look at the special case and see what comes out for this plot in this form. X equals amplitude times sine omega t, which I could write as amplitude sine 2 pi over period times the little time t. All right. So I'm going to plot this on these solid axes, which I've shifted over by 1/4 of a period. So as times the x-axis, well, that'll still be here. So this is still x equals positive a. This is still equals x equals negative a. This is still, this level here is x equals 0. But for time, we'll start 0 here. This will be 1/4 of a period. This will be half a period, 3/4 of a period, 1 full period. So we just shifted by 1/4 of a period. OK. So first, let's figure this out. Then we'll plot the points. So looking at this function, x equals a sine omega t, or x equals a sine 2 pi over capital T times little time t, little t for time. Plug in 0 for little t. I'd have 0 in the argument. Sine of 0 is 0. Now let's plug in capital T over 4 for little t. So 2 pi over capital T times capital T over 4. That'll give me pi over 2 in the argument of the sine. Sine of pi over 2 is 1. 1 times a gives me a. So let's plot those points. When the time, little t is equal to 0, x is equal to 0, we're now on this solid axis with these numbers up here representing the time. So time 0 is this, and x is equal to 0. So there's our first data point. Then, when the time, little t is equal to pi to 1/4 of the period, the position x will be equal to the amplitude. So we'll have this point here, whoosh, same point that we had before. When the time is equal to half a period, the position x will be 0 again. I'll just mark that there. When the time is equal to 3/4 of a period, the position x will be equal to minus a. Put that right there. When the time is equal to 1 full period, the position x will be equal to 0. There we go. So you can represent the position as a function of time for a system in simple harmonic motion with a cosine function or a sine function. Now, what I've done here is I've shifted the axes, but if you wanted to use the same set of axes, then you could shift the argument by a quarter of a period. We could also consider in-between situations that don't align either of these by putting some other value of phi in here, or theta plus theta, add that to this in here. All right, along the way in illustrating this, we demonstrated that this parameter omega, which is multiplying a t in either a cosine function or the argument of a sine function, is indeed the angular frequency, which is related to the regular frequency and also related to the period. Thank you.